Welcome to another lecture on molecules in motion, and in this, as we have discussed so far, in the last class also I was talking about this, that we have talked about the conductivity, molar conductivity of a strong electrolyte. What we are going to what we have seen according to the Colorocious law, the molar conductivity of a strong electrolyte varies linearly with the square root of the concentration. If you remember, this was the expression we had, that was the molar conductivity at any concentration was equal to the molar concentration conductivity at infinite dilution minus k under root of C. So, we have a square root of concentration dependence of the molar conductivity. We had also seen that if you plot the molar conductivity under the square root of the concentration, this concentration is moles per liter, and if you get a straight line at very low concentrations, and we can find out the value of the lambda naught, that is the molar conductivity at 0, almost tending to 0 concentration of the electrolyte. If we extrapolate this plot, then wherever it intersects the y axis at corresponding to 0 concentration, we label that as the molar conductivity at infinite dilution. So, what we have seen that the molar conductivity is proportional to the square root of the molar concentration of the electrolyte. As the concentration of the electrolyte approaches 0, then the molar conductivity approaches the molar conductivity at infinite dilution. Okay. This is what we have seen. This is some sort of a behavior which we need to account for. Why is the molar conductivity of a strong electrolyte dependent not on the concentration, but under root of the concentration of the electrolyte. So, if we go look into this, a number of scientists have tried to explain the behavior of the strong electrolyte, and these are some of the scientists: Noyes and Sutherland, Burgum and Neilmer. These are, if you see, in the 1960s, within 1912, in the first within 10 years of each other, we have some sort of explanation by the scientist. But the major breakthrough was when two scientists, Peter, what we have is Debye Huckle. So, Peter Debye and Eric Huckle were the two scientists who successfully attempted to explain the behavior of a strong electrolyte when we have dilution. What was the Debye-Huckle theory? Whatever we have, we are going to be looking into the Onsager equation, which is a further modification of the Debye-Huckle theorem or the law which we have established. So, before we go into understanding what is the what are the things which we have added when we are talking about the Onsager equation, before that let us talk about the Debye-Huckle theorem. What was the observation? The Debye-Huckle theorem, the main observation which was explained was by Debye-Huckle theorem is the activity coefficient of ions. When you have ions in solution, we are expressing the activity of the instead of concentration, we have activity coefficient of the ions, activity of the ions represented, where you have the concentration equal to activity equal to concentration into the activity coefficient, if you remember. So, what the explanation was given by Debye-Huckle theorem or the theory is the activity coefficient of ion, which are ions in solution, the electrolytes, in the limit of low concentration also showed a square root dependence on their ionic strength. And they also found that they depended on the type of charge that was involved, not the specific identity of the charge. So, let us now understand what the Debye-Huckle theory for a strong electrolyte was supposed to be. So, for a strong electrolyte, we all have discussed this before. For a strong electrolyte, the ions are supposed to be completely dissociated in solution, and the solution itself, the composed of the solute and the solvent, is supposed to be having electroneutrality. There is no going to be a net positive or negative charge. We have the solution maintained at they are electrically neutral. If we talk about a ideal solution when you have a solute the electrolyte in a solvent, the ideal solution will be having the uniform spread of the charge throughout the solution. But what Debye-Huckle proposed or interpreted as then he formulated the theory is the long range and the strength of the Coulombic interaction is the main reason for the solution to deviate from their ideal behavior, and this is the basis of the Debye-Huckle theorem. Okay. So, opposite charge ions attract each other. We have the anion whenever we have a solute electrolyte dissolved in a solvent, they will dissociate into positive and negative ions. So, opposite charge ions attract each other. What happens? The anion is more likely to be found near a cation in a solution and vice versa. And in the form, they form a shell sort of a thing, which is a sort of a haze of opposite charges around a central charge. Okay. So, this haze, which is supposed to be symmetric around a central charge, actually screens the charge of the central ion. So, what we are looking into? We are looking into something like this, where this is the distribution of ions in solution, and you see the positive charges are majorly surrounded by the negative charges, and this charge, this is a central charge, this is the central charge, this is a negative charge which is surrounded by a positive haze, and a positive charge is surrounded by a negative haze. So, the overall solution is electrically neutral, but by any given ion you will have at any point any given ion will have excess of counter ion, opposite ion surrounding them. And if you take a time average of counter ions are more likely to be found near the given central ion. If you take a time average, the spherical sphere haze which we are looking into, see I have demarcated this as a blue haze, and this haze around the central ion of the counter ion here outnumbers the central ion, and the net charge is equal to the magnitude, but in opposite to the central charge of the central ion. So, what we have, you see the time average, these are the dispersions of the ions which we have. If we take a time average, take a time shot, and we are likely to encounter a haze of oppositely charged ions against a central ion of opposite charge. If you have a central ion of positive charge, that is going to be surrounded by negative charge in a spherical manner. Okay. And this haze around the central ion, this can be a negative ion as well, then you will have the positive ion haze around it. Always we are seeing that the number of counter ions are surrounding the central ion is going to be outnumbered. The haze forming the ions forming the haze around the central ion will always outnumber the ion in the center. That is what we are seeing in this dispersion as well, and this one as well. Okay. whether it is negative ion or positive ion, they will be surrounded by a haze of oppositely charged ion, which will have which will be more than the outnumber the number of the central ion. If central ion is 1, we see a surrounding at least 4 or 5 ions here. So, this haze, this symmetric haze around the central ion taken on over a time average is known as the ionic atmosphere. Okay. So, what happens according to Debye-Huckle theory, what they have found, the energy of the screen central ion is lowered as a result of interaction of the ionic atmosphere. You see, if you are looking into the picture, you will see this ion and this ion, the Coulombic interaction between these two ions, this is a positive charge, this is a negative charge. This interaction is going to be affected if you have a shield around it. So, this haze of the oppositely charged ion across the central ion is actually shielding this ion from this ion, right. In the process of shielding, what happens, the energy of the screened central ion is lowered as a result of interaction of ionic atmosphere. The ionic atmosphere is actually interfering the intercoulombic interaction between the positive and the negative ions placed in the solution. And Debye-Huckle theorem sees that if you have some amount of energy before and then you have some amount of lowering of energy, this difference in energy which is lowered due to the interaction of the ions with the of the ions with the ionic atmosphere, this difference of the energy which is lowered because of the screening of the central ion by the ionic atmosphere. So, the central ion now, if I have at one point of time where there is no ionic atmosphere, a haze around the central ion, that condition and the condition where you have the ionic atmosphere existing, you will see when you have, it was shown that experimentally it has been shown that you can have a lowering of the energy of the central ion when they have a ionic sphere around them. So, this difference in energy of the central ion which is lowered, this difference in energy was found to be proportional to the ionic activity coefficient of the electrolyte. And according to, I am not discussing the Debye-Huckle theory in detail, but I am just giving you the gist so that we can proceed as to what is the modifications which we have when we have Debye-Huckle-Onsager equation. So, the Debye-Huckle theorem says that the central ion of in a ionic electrolyte solution is going to be, energy of the central ion is going to be lowered because of the presence of ionic atmosphere, and this lowered energy amount which is lower, the difference in the value of the lowered energy is proportional to the ionic activity coefficient of the electrolyte. Okay. So, this model led to the result that at very low concentrations of the electrolyte, the activity coefficient of the electrolyte can be calculated by the Debye-Huckle limiting law. It is something very beautiful that based on this conditions in physical conditions of physically viewing this as a central ion being screened by the ionic atmosphere, we come up with a beautiful equation which is more or less valid and with whatever we see in experimental results. So, if in the very dilute conditions of the electrolyte, if we have the expression derived from the Debye-Huckle theory, it states that the activity coefficient of the electrolyte is going to be proportional to the ionic root over of the ionic strength. So, this is the mean ionic activity coefficient of the electrolyte which we are dealing with. So, if we have something like this, what is happening? We are seeing this, this is the expression which was, this is the model. Try to visualize this. We are trying to, we have seen some experimental result. What Debye-Huckle was trying to do, he was trying to fit a model to match whatever experimentally was observed, and for that he has given an equation. Okay. So, the Debye-Huckle limiting law is the equation which he has formulated to explain the behavior of a electrolyte at very dilute conditions. Okay. So, if it is a very dilute condition, only then these things which we are seeing is more relevant. We have the lowering of the energy of the central ion because of the ionic interaction, ionic atmosphere present around them, which is screening the neighboring ions in the solution. This lowered amount of energy was proposed to be proportional to the mean ionic activity of the electrolyte, and that expression was summarized something like this, which was a formulation by Debye-Huckle, and this was considered to be valid only with very low concentrations of the electrolyte, and hence this equation is known as the Debye-Huckle limiting law. So, we have here in this expression, this is a constant, this is for a aqueous system at 25 degree, we take it as 0.509, and I is the ionic strength of the solution. And how do you calculate the ionic strength of the solution? Ionic strength is nothing but the summation of the charges. Z is the charge of the ions which are present. Suppose I, a number of ions are present, the contributions of each ion has in the solution has to be taken. So, the charge square of each of the ions, positive or negative ion, and multiplied by the molarity of the, here you are not talking about the molarity, we are talking about the molality of the solution. That means 1 kg of the solute in a grams of the solute in 1 kg of the solvent. So, everywhere you have a expression of mu naught is the expression in say for we have some sort of molarity here per kg of the solvent. Here we have 1 gram per kg of the solvent. This is usually taken to be 1. Okay. This is usually taken to be 1, and it is a standard value for when we define. Usually we do not even write until we have difference in unit, in we are not expressing in molality. Then we can use some other ways of representing the MO naught. MO naught is the concentration of 1 gram of the solvent in 1 kg of the 1 gram of the solute in 1 kg of the solvent. So, essentially this is taken to be 1. Okay. So, we may ignore it if as long as all the equations which we are dealing with is having the same units of molality. So, here what we have, if you have say 2 different types of ions having, each will have a molality of equal, M plus will, if they are 1 electrolyte, then M plus and M minus will be the molalities of each of the ions, and then the ionic strength will be represented as something as the molality of the plus ion into the charge of the ion which we are talking about, and then the molality of the minus ion into the charge square of the minus ion divided by m naught. Usually, we will take this m naught as to be 1. So, you see the ionic strength emphasizes the charge of the ions, because the charge here is having a square power. So, if we want to find out, there is a table which I can show you. If we want to find out the ionic strength, the relation between ionic strength and molality of a particular electrolyte, we can use this sort of a table. See what we have? We have the ionic strength and the molality represented as I into K into m by m naught. M naught we will take it as 1. Okay. So, suppose we have different type of electrolyte, 1 electrolyte, this is 1 electrolyte, this is the cation which is going to be generated, this is the anion which is going to be generated, this is the cation which is going to be generated, this is going to be the anion which is generated. For example, we take a electrolyte which is M2X3. M2X3 solution molality, say let us that the solution molality be M. Then what do we have? So, we have what are the ions which is generated? We have M3 plus and X2 minus. Okay. This is going to be the M3 plus and X2 minus in the solution. So, let us see from the table what should be the value. I have M3 and corresponding to the anion will be X2 minus. So, this is my factor which I get 15. So, 15 into the molality of the solution whichever electrolyte we have. If we know that, then we can apply that here and we can find out the ionic strength. Okay. So, the ionic strength and the relation between molality can be used to find for various types of electrolyte. What we have in just found out that the ionic strength has a under root of ionic strength dependence can be explained on the properties of the ions surrounding each of the central ion. So, based on this we can see that whenever we are having a electrolyte solution, if we want to explain how the behavior of the electrolyte in terms of the ionic coefficient, mean ionic coefficient, if we know the mean ionic coefficient, we can find out the relationship between the mean ionic coefficient and the ionic strength. So, the ionic strength dependence, instead of we are not talking about the conductivity, we are or molar conductivity, we are talking about the mean ionic coefficient relationship with the ionic strength, and this was explained by Huckle in terms of the ionic atmosphere in presence of present across the central ion. To explain the Colorocious law's dependence of square root of concentration of the molar conductivity, we can use a similar logic. So, whatever we have, whatever was developed by the Huckle theorem could be proposed to be extended to explain the molar conductivity dependence on the concentration in terms of square root of the concentration, which concentration was in moles per liter. So, this explanation can be based on whatever we have judged from the explanation for the ionic for electrolyte, where you have ions and that you have a ionic strength dependence, square root of ionic strength dependence in terms of the activity mean activity coefficients of the ion.